Right, so it's a great pleasure to have Duncan Dauvergne from Princeton, who is going to tell us about learning from the directed landscape.
Okay, great. Yeah, thank you very much, and thank you to all the organizers for the invitation. So I'll go ahead and share my screen and then get started. Okay. Okay, yeah, so the talk is about this, what's called the directed landscape. So this is a random metric on the plane, which I'll describe in a second. And this is based on a couple of papers. The first one is was joint work with Janos Ortmann and Virag, where we constructed this object a couple of years ago now. And then what I want to get to, sort of after going through the details of the construction, is some more recent work with Lingfu Zhang, where we in some sense construct we construct an extension of the directed landscape. But really, I think of this as sort of the new work is, gives some concrete ways of understanding certain things about the geometry of the directed landscape. And it allows you to understand sort of, somewhat surprising Brownian structures of geodesics and things like that. So let me go ahead and get started. So I'll start with kind of a universality picture here. So take a random planar metric. So for example, this is you just look at Z2 and you put IID edge weights on the edges in Z2 where their IID equal to either 1 or 2. And then you look at distances in the corresponding graph with random weights. Okay, so this is sort of a simulation that Malin did of this. And you can ask, well, what does this sort of random planar metric look like when the distance between these points sort of tends to infinity? So this is the picture of what should happen for such models. So I'm going to look at distances that are between points that are roughly order n apart. So my points are going to be kind of order n apart. Or this is the distance order n, rather. And I'm also going to sort of look at points within all distances within a strip of kind of order n to the 2/3 width here. Okay, so this is the picture. So you kind of order n apart. So that's my second coordinate is representing the general distance between the points, and I have a strip of order n to the 2/3. And what you should see for these sorts of models is some sort of mean term. And then the fluctuation term here should be of order n to the 1/3. And then there's a fluctuation term of order n to the 1/3. And the fluctuation term is some random function L of x, s, y, t. So it sort of should be a random limiting directed metric. And this L, this is kind of like the idea here is this should be like a central limit theorem. So regardless of sort of how you structured your original random metric, you should always see, your mean term will be different. You might also have a term that depends on x and y, but the fluctuation term should always be the same universal object, which is this directed landscape, which I'll talk about today. And this is, we're working kind of within the KPZ universality class. And in addition to kind of seeing this stuff for, seeing this limit for random metrics, it also should show up in situations like random polymers, things like the KPZ equation, things like TASEP, sort of random interface growth. So it's sort of, all of these are situations where you kind of have a hidden random planar geometry. Okay, so how do you actually get to constructing this directed landscape L? So the model that I wrote at the start is kind of highly intractable in some sense. So you need to start with a really tractable integrable model where you can say a lot. And the model that I'll choose to work with is called Brownian last passage percolation. So the idea is that we're going to define path lengths according to some sort of Brownian noise. So there's a formula for defining path lengths, but everything's kind of easier to understand through a picture. So I have my paths, which are, say, Bn on the bottom up to Bm, and I have some Bi in the middle. And I'll just superimpose the graph of I'll look at the graph of pi sort of superimposed on top of these Brownian motions. So it's going to look something like this. So my functions pi are always going to be paths that they're going up in the way that I'm drawing them, but they're kind of going down in terms of the indices. It's just some funny, there's some logic with the indices where you kind of want your indices with higher indices lower down and lower indices higher up, so some sort of matrix coordinates. Okay. And so the path length is just the sum of all of the increments I see when I kind of superimpose the graph in this way. Okay. So now we have a nice notion of path length. You can now use this notion of path length to define kind of a notion of distance. So, normally if you're defining distance from path length, you would say a distance between a pair of points should be the length of the shortest path. Because kind of for historical reasons with last passage percolation, we define the distance to be the length of the longest path. I mean, it's kind of clear when you do this with Brownian motions that there's a clear symmetry in terms of, a distributional symmetry between the length of the shortest path and the longest path here, but we're always going to work with the length of the longest path. Okay. And because our paths kind of only go in one direction, we're only going to define distances between xm and yn, where the xm and yn are in a particular order. Okay. So this is my Brownian last passage value. And the right way of thinking about this, or at least for the purposes of our talk, is going to be thinking of it as a directed metric on R cross Z. So it's metric-like. It's directed in the sense that you don't assign distances to every pair of points. You only assign distances to pairs of points in a certain order. And I'll call a path that achieves this supremum a geodesic. Okay, so then what does our main convergence theorem for Brownian last passage percolation say? Okay, so again, you're going to see this 1, 2, 3 scaling here. So if I look at the distances between points that are sort of order n apart in the number of lines. We kind of have order n is the distance in the number of lines, as I've drawn before, and then we're also going to vary what I'll call the spatial coordinate back and forth by n to the 2/3. So then if you look at these sort of Brownian last passage values, now we can say that you actually see this heuristic that I put up before, where you have a mean term, which now depends on t, s, y, and x, plus a fluctuation term, which is a random function L called the directed landscape. And in terms of the way this theorem is stated, I'll mention something about this error term, though it's not super important. Basically, this error term is kind of, you think of it as a random function, and in distribution, this random function is converging to 0 in the uniform uncompact topology. So it's sort of a fairly strong notion of convergence here. It's a functional convergence. Okay. So what is this directed landscape L? So it's going to be, you think of it as a metric. So it's assigning distances between what I'll call space-time points, so x, s, and y, t. So the two coordinates were kind of playing very different roles in the prelimit, because the coordinates were sort of order n apart, and for the other coordinate, you're kind of order n to the 2/3 apart, and this is the same in the limit. And so you sort of have distances between sort of x, s, and y, t here, and you're only allowed to move forward in your time direction. You can move back and forth in your space direction, but only forward in your time direction. So you only assign distances when s is less than t. Okay. But if you just think of this, if you kind of forget about the metric structure here and just think of L as a function, it's still a nice continuous function. I mean, it's not regular. It's sort of slightly less than Holder 1/3 in time, and slightly it's actually kind of locally Brownian in space. But so it's nice and continuous, and you can do lots of things with it. Okay. And the first thing we're going to want to do is, it's a metric, and you can use this, or it's a metric-like object. You can use this object to define a notion of path length. So because we can only move forward in time, we should think of our paths really as functions. So a path is going to be a function from a time interval to r. And so at each point, so a path here is a function from a time interval into r, and you kind of think of these locations in the plane as being the point pi of r comma r. And we can then just define this length of the path by subdivision. So we just approximate the length by taking finer and finer partitions and summing up the distances between points here, and so on. Okay, so it's just like defining the length of a curve in Euclidean space by a piecewise linear approximation. Okay. So we say that a path pi is a geodesic if its length is just the distance between its endpoints. Okay. And this is one way that we know that this is like the right notion of geodesic is these are actually limits of the geodesics that you were seeing in Brownian last passage percolation. So it is kind of the right notion. And you should think of this L is also very rough. So if you do this procedure for, say, any deterministic path, so if you ignore the randomness coming from L, do this procedure for a deterministic path, you're always going to get that this length is negative infinity. So for most paths, most paths are going to be terrible when you try and travel along them, but you need to choose a well-chosen random path which depends on this kind of background metric L in order to see something with finite length. Okay, so how do you build L? So the idea is, this is we have some complex random metric and we want to try and reduce the problem of building this to something a bit simpler. Okay. So the thing to do is kind of recognize a couple of properties that this directed landscape is going to have. So the first is an independent increment property. Okay. So let me kind of go back to the Brownian last passage picture. If I have times, say, S, R, and T, like this, and or maybe lines Sn, Rn, and Tn, something like this, and I look at my Brownian last passage values from this line up to this line, and from this line up to this line, well, these use independent sets of, these are generated with independent sets of Brownian motions, okay? And so, of course, these two Brownian last passage values have to be independent between these two lines, and the same thing goes through with the landscape. So you have independence on disjoint time intervals. Second, you have what was a semi-group property for the landscape, or I'll call it a metric composition law. So now suppose you fix 3 times S, R, and T. And say I want to understand last passage or the landscape value from line or time S up to time T. Well, what I'm going to want to do is, this is going to be achieved by some path that goes through the time R. And so, how do I get the length from here to here? Well, it's going to be the best possible value of a length from here to some point on here, plus this point to there. So you have this metric composition law where L of XS YT is just the max of L of XS ZR plus L of ZR YT. Okay. And if you think about what these two properties allow you to do, so if we think about the joint distribution of L going from, say, S to R, R to T, and S to T, well, the first two guys are independent, and the third is just expressed in terms of the first two guys. So these two properties tell you that you can basically get all joint distributions just by knowing the distribution of L going from one time to another time. And finally, you have, L is a scaling limit. It has a bunch of, it's going to have certain translation and scale invariance properties. And so what these properties tell you, so you should, again, I've written these distribution inequalities, think of them as joint in X, S, Y, and T. What they tell you is if you want to look at the landscape value from time S to time T, this is always just going to be a rescaled version of the landscape value from time 0 to time 1. And so the fourth property in this list, which characterizes L, is just the law of the random function going from time 0 to time 1. And this is kind of, was the big obstacle in constructing this object is, how do you make sense of, or what should this object be? This what's called the Airy sheet, which is the random function, where you're just allowed to vary your two spatial coordinates and your times remain fixed. So how are we going to try and understand this Airy sheet? Well, the starting point is, which is in some sense the root of how most or many interesting results in last passage percolation are proven. And we're going to go back to some integrable combinatorial structure, which is this RSK bijection. So if you've seen the RSK bijection between an array of, say, or a matrix with non-negative integer entries and a pair of Young tableau, then this might look slightly different. It really is the same thing. It's just kind of disguised, and it's a continuum version. Okay. So first, I'm going to define something called multi-point last passage value. So what is this? Again, it's kind of best drawn through a picture. So say I look at line n and line 1, and I have points, say x1, x2, x3 here, and maybe y1 and y2 equals y3. So these are vectors x and y. I can define a multi-point last passage value is just going to be the best possible sum of path lengths between these points, where I specify that my paths have to be disjoint. So this is what's going to separate it from just a sum of usual last passage values as I enforce a disjointness condition. Okay, and because I'm now going to be focused on understanding this Airy sheet where we just vary spatial coordinates, I'm always going to go from line n to line 1. So everything now is from line n to line 1, so I'll just kind of omit these line indices. Okay, so we can use this multi-point last passage to construct basically an RSK bijection. So this is going to be a map from, you take n Brownian motions, B1 through Bn. So you can actually just think of these, they don't need to be two-sided now. They're just going to be functions from 0 infinity to r, Brownian motions from 0 infinity to r. And we map them to a collection of functions W1 through Wn, which are defined through the following formula. So this is the sum of the first k wi of y's is a Brownian last passage value from a cluster of k points at 0 to a cluster of k points at y. So we can kind of think about what this means. So what does this say about W1? So this says that W1 of y is just the Brownian last passage value from 0 to y. Again, always going from line n to line 1. So what does this look like? Well, it's just going to be kind of just increases like that. And then W2 is what you get, W2 plus W1 is what you get when you do this with a cluster of 2 points. And so you should think of W2 as kind of the additional gain from adding an extra disjoint path. And so this is never going to be as good as what you got from the first path. And so you have this diminishing return story where W2 is kind of, W2 is a bit less than W1, and then W3 is less than W2, and so on, all the way down to Wn. So you should think of this as what our RSK map is doing, is it's taking a bunch of independent Brownian motions and producing on the other side a bunch of ordered functions, W1 through Wn. And there are a few remarkable facts about this. And the kind of first one is due to O'Connell and Yor, which says that this W, we can actually really understand its law. So it's just given by n Brownian motions, condition never to intersect. So in other words, it's the same thing as a Dyson's Brownian motion. So it's just the eigenvalue process for a Hermitian matrix value Brownian motion. And so, this is a really tractable object. It's really understandable. You have nice determinantal formulas, and so you can start taking limits of this W. The other thing I'll mention here is I said this is an RSK bijection. So what turns out to be true is that almost surely, if I give you this W, then almost surely you can actually go back and construct what your original Brownian motions be. It's not deterministic at this level because I somehow lost a little bit of information, but you can still go back almost surely. Okay, so I said this melon is, or this, I'm going to call W sometimes we call it a melon because these non-intersecting Brownian motions look a bit like stripes on a watermelon. So this melon, like I said, it's tractable. You have determinantal formulas, and you can do some analysis. And so in a slightly different model, this analysis was done by Preoffer and Zhang, where they proved that W converges in sort of a finite dimensional distributional sense. And then the theorem I'm writing up is due to Corwin and Hammond's stronger convergence theorem. So what is this? And again, everything's kind of best understood with a picture. So I'm going to look at a scaling window of my melon around location n in an order n to the 2/3 window, with an order 1 number of lines. Okay. And then when I take a limit here, I get the following picture. I just essentially, we had finitely many non-intersecting Brownian motions. In the limit, you basically get infinitely many non-intersecting Brownian motions. So you get this limit, which I call this. I'm using this kind of script W notation. And this is called the parabolic Airy line ensemble. So the way you should think of this object is it's exactly infinitely many non-intersecting Brownian motions that kind of decay parabolically as you go down to infinity on either side. So this is kind of pulling the Brownian motions down. But the non-intersecting property, the fact that the top ones need to avoid infinitely many Brownian motions down below, in some sense, is also pushing the Brownian motions up. So you somehow have this pull down of the parabola, and you have this push up from the non-intersection property. Okay. And in terms of what this says about last passage, well, W1 is going to be the landscape value from the point 0 to, I need to make sure these match, to a point at line 1. So this is somehow giving you like half an Airy sheet. This tells you if you vary one spatial coordinate, what do you expect to see? Well, you expect to see this, limit of the top line of the melon. You expect to see this W1. Okay, so the question is, can you somehow go further? Like, what more can you say about last passage, or about the limit of Brownian last passage percolation from this melon result? In particular, it seems like right now, what we're saying about last passage is only using the top line. Is there more information contained in those other lines? And the key starting point for this is what I'll call I'll call this the RSK isometry. So this was something that my co-authors realized was true, and then kind of much later on we realized this was true, and we really were able to do a lot with it. And then much later on we realized that the ideas for this isometry, not in the exact form that I'm stating it, are turned out to be available in some long ago, or not long ago, but 15 years, a long time for me, papers of Naomi and Yamada and Bian Boucherol and O'Connell. Okay, so what does this say? Is basically, if I look at last passage across my original Brownian motions, then this is the same as last passage across my melon W. So you somehow, these sort of last passage values are the same as these kind of last passage values here. This is true for any number of points. This is true at the multi-point level as well. So this tells you that not only is RSK a bijection with a really tractable image, but it's also an isometry. So it should be really, really good for doing probability. So you can ask, well, what can you do with this isometry? And when you first think about it, it might not seem like it's the most useful thing, right? Because originally we're doing last passage across Brownian motions, which are independent. And then we're translating this to last passage across a bunch of correlated functions. And so it should be, in some sense, more complicated to analyze last passage across these correlated functions. But it turns out there's some structure that's kind of saving you here. And what happens is that the geodesic branching structure is somehow much simpler in W than in B. So let me say how this works. So let me draw roughly what the geodesic branching structure looks like in B. So this is my, if you look at geodesics across your original Brownian motions, from say 0 to n and 0 up to n to the 2/3 and all the times in between, then you see a tree, and you'll see a bunch of branch points on the tree. And all of these branch points live in the bulk of the Brownian motions. Now we can try and see what happens in the melon. So if we do this in the melon, your paths are now ordered. So the fact that your paths are ordered means that the geodesic from 0 to any point is just going to want to follow the top line. So it just does this. So you had a complicated branching structure, which is now completely trivial at the level of the melon. Okay, this is somehow, what I'm saying is not really that interesting. We already know that last passage from 0 sort of survives the limit and is contained in the parabolic Airy line ensemble. But now we should try doing this not from 0, but from a nearby location, say x times n to the 2/3. And the picture that you expect to see is the following. You know, these trees they'll have some branching points which are different, but certain branch points should coincide for the green and purple geodesic trees. And so while the branching structure isn't all contained on the top line, when you go to the melon, it somehow should still be related to this branching structure coming out of 0. So it does get much simpler. And the precise thing that happens is that all of the branching takes place in the top corner. So all of your branching is taking place in a window, which is sort of order 1 in the number of lines versus order n to the 2/3 in space. So what this is telling you is that all of your branching structure occurs in a window that still is there in the Airy line ensemble. So what does this tell you? So that means that differences of last passage values are just differences of last passage values from a particular branch point, right? And because these branch points are surviving into this Airy line ensemble limit, you might hope that these differences of last passage values also survive into the Airy line ensemble limit and are somehow contained in there. And you know, there's a lot of, you know, this is really a fuzzy picture. There's a lot of work to make it into rigorous mathematics, but you can basically do this. And this is how you construct the Airy sheet. This is how you're able to start varying that second coordinate. Okay, so let me say what the Airy sheet construction theorem is. So basically, what is your Airy sheet? Well, it's uniquely characterized by two things. First, you have a translation invariance, something you can easily check that you expect because you have translation invariance of Brownian increments. Second, that differences of Airy sheet values, which again, differences of Airy sheet values are like differences of last passage values. These correspond to differences of Airy line ensemble last passage values. So these things are basically just differences of last passage values in the Airy line ensemble. And the key point here is, what differences do you take? And it turns out that the right difference to take is the difference depends on your starting point x. You should take a difference from this point xk lying on a particular parabola. So what the picture here is kind of, these points here are approximately xk, this point down here. And sort of as you take k to infinity, you recover the true difference. Okay, so you know it's a somewhat complicated thing, but the idea is just that this branching structure is what survives into the Airy line ensemble limit.
Can I ask a question?
Yeah, sure.
So is there an intuitive way to understand why the branching happens along the top?
For this first picture here, just the blue branching, or
yeah, the purple box. Why is it?
I think there. Maybe I can say something about it afterwards. I think there are a couple of intuitive ways to understand it. Well, one thing that you can do is you can think of. I kind of don't have a good explanation that would take less than 10 minutes or so.
Okay.
I have some intuitive ways to understand it that didn't end up actually, turning into a proof. But it has something to do with maybe we can talk about it afterwards if you want to. Yeah, because I think it would take a bit long.
Yeah, thank you.
Okay, so we have this theorem, and maybe it's not completely obvious from the setup here, but it turns out that what this tells you also is that the Airy sheet can actually be expressed in terms of the parabolic Airy line ensemble. So at least when I restrict my choices of x to non-negative x. Okay, so let's think about what we've done so far and what we can do with it. So basically, we've shown that there's a correspondence between the directed landscape and the parabolic Airy line ensemble, which at some level looks like this. So this is basically for all x greater than 0, or greater or equal 0, that landscape values correspond in some sense to like a last passage value in the Airy line ensemble from x infinity to y1. And the question is, you can ask, does this correspondence extend further? And what information can we actually extract from it? Can you get some really good stuff from this? And I think the natural place to start here for answering both these questions is by trying to take not the limit of just single point last passage, but the limit of the whole multi-point isometry. Okay, and see what you get by doing this. Okay, and so this is now what Lingfu Zhang and I did in more recent work. Okay, so how are we going to try and take the limit of the multi-point isometry? Well, let's first try and think about what the natural limiting object should be. So the natural limiting object should be something like multi-point last passage value across the parabolic Airy line ensemble along sort of asymptotic paths in some sense. So we have to make sense of what that means. Okay, so the first thing is I want to define actual path lengths in W. So my paths are now my paths are going to be infinite, and they're going to be infinite with a particular direction. So they're kind of infinite. They have this parabolic shape, and their direction is corresponding to where they would have started in the melon at some location x. So I'll call a function satisfying this limiting property a parabolic path from x to y. And how am I going to try and define the length of such a path? Well, the best possible length should be your last passage value. And that's just the Airy sheet value. So we're going to start by, saying, okay, the length should just be the Airy sheet value. But we should have a correction of this Airy sheet value, which is, how close did our path get to the best possible path? And so how do we express this? Well, basically, you're just going to truncate your path and see, well, how close is it getting to the best possible path on every finite segment? So you kind of estimate, well, this term in here is how close was your path to the actual last passage value between its endpoints. Okay, so this is sort of a discrepancy. This is some, this thing is something which is less than or equal to 0, and it's actually, as you take z to negative infinity, it's always decreasing. So this limit always exists, and this gives you a good notion of path length. And again, it's the kind of thing where if you do this construction for a deterministic path, you're always going to get a length of negative infinity. But if you do this construction with a well-chosen random path, you can, in particular, you'll always find some paths which achieve this S of xy, and you'll find lots of other paths with finite length. So this notion, now you have a notion of path length, you can define a notion of last passage. So basically, how are we going to define multi-point last passage? Well, we'll just say that the multi-point last passage value between 2 points is the sup over sums of path lengths, where the sup is over disjoint parabolic paths. Okay. So this allows you to take kind of the full scaling limit of multi-point last passage percolation. So I'm looking at multi-point last. So this theorem says that if I try and take the scaling limit of multi-point last passage percolation from now a vector x to a vector y, then up to a mean term, what I see is some random function s of xy. We call S the extended Airy sheet. So S takes values of, S, its domain is all possible pairs of ordered K tuples X and Y. So it's kind of this funny domain. Oh, that's going to take a while to go back. And of course, if you just look at S restricted to single points, so S just restricted to R2, this is the usual Airy sheet. Okay. And of course, the way that we get this construction is we prove that S of X, Y is the same thing as this Airy line ensemble last passage from X to Y. Okay, and this really, you should think of this theorem as being the limit of the multi-point isometry. So previously we kind of had the limit of a single point isometry. Now this is the limit of the multi-point isometry. So now you have a notion of an extended Airy sheet. Before we had built up this directed landscape from a bunch of independent Airy sheets. This was sort of our 4-point construction before. You can do the same thing with extended Airy sheets, and you get an object which we'll call the extended directed landscape. So this is the extended directed landscape L of X, S, Y, T. And you can ask, well, when you do this, you should expect a couple of things. First, just like the extended Airy sheet was a scaling limit of multi-point Brownian last passage between two fixed lines, this should be sort of a full scaling limit of multi-point Brownian last passage. So this is, and this is actually not very hard to check once, beyond satisfying some technical tightness things, this is not hard to check. The second thing is, this is also something you should expect, which is that you can express the extended landscape in terms of the original directed landscape. So what should you have? Basically, if I want to look at, say, the extended landscape value from X1, X2 up to Y1, Y2 at some fixed times X and T, I should just optimize over sums of disjoint paths in the original directed landscape. Okay. And it turns out that this is the case as well. The extended landscape is related to the original directed landscape in this way. It's kind of unsurprising. This is basically saying that multi-point Brownian last passage converges to multi-point landscape last passage. But maybe while I said the first theorem here is kind of quite straightforward to show that this kind of part is straightforward, the second part is, I'll just say it's quite hard. It's really not obvious that these two constructions are the same, and you kind of need to do a lot of work and develop kind of a detailed understanding of what exactly these multi-point last passage values across, or multi-point last passage across parabolic Airy line ensembles, what that actually looks like. So there is kind of a lot of work to do for the second one. Okay, but now we kind of have this construction, and at this point you might think, oh, this is just kind of in the level of something a bit random. Well, we had a multi-point isometry, so we can take a limit. But the point is, I think this actually tells you a lot of interesting things about the directed landscape. So this is, I'd written up this slide before, and now I want to address the second question, which is basically what information can we extract from this extended version of the correspondence? Okay. So here's our extended version, which just says that L going from X0 to Y1 is the same as this, W from X to Y. And now we can think about something. So I claim this gives you a way of analyzing geodesic disjointness, for example. So consider the following. So take points X1, X2 and Y1, Y2. So I'm just going to do this with pairs. You could do this with K tuples. So what would it mean if there are disjoint geodesics in L between these points? So if there are disjoint geodesics, so this is X1, X2, Y1, Y2, so this is the picture. This is the exact same thing as if the multi-point landscape value was just the sum of the single point values. Okay. But now by this isometry, this is the same thing as the multi-point value in W being the same as the single point values in W. okay? And now this is true if and only if you see disjoint geodesics between the corresponding points in the parabolic Airy line ensemble, okay, along parabolic paths or whatnot. But now this is sort of really quite remarkable, because we took a complicated question, which is understand disjointness of geodesics in this, kind of difficult continuum object, the directed landscape. And we've exchanged it for a much more tractable question, which is understand disjointness of geodesics across lines that are essentially just Brownian motions. So that locally these things are Brownian motions. So we've sort of exchanged something which is really quite continuum for something which is semi-discrete. And you can use this to prove some really interesting things. So let me give you an example. I'll define the gap process of my parabolic Airy line ensemble, which is going to be the difference of the top two lines. So this is my W1, this is my W2. And my gap process G just goes between. And I'll define this set ML, which is just, I wrote it up with a formula, but it's probably easier to explain in words. These are just points, maybe points here, where you see a one-sided, where you see a left-sided local minima. These are my left-sided local minima for the gap process G. This is because everything is local, because this gap process G is actually a locally Brownian object. This is sort of a Hausdorff dimension 1/2 set, for example. So what you can show is that almost surely this set ML is equal to the set of points for which there exists a disjoint geodesic in L, I should say in L, from 0, 0 to y1 and from z0 to y1 for some z greater than 0. So I think let's try and draw out what this is actually saying. So ML is the set of points y. So these are set of points y. So let me draw an example. Where there's a disjoint, where there's a geodesic from 0 to y, and also for some large z, these two geodesics are genuinely disjoint. So what you usually expect to see is that these two things should coalesce. For typical values of y, no matter how large you take z, you'll see a little region of coalescence. But these exceptional points, sort of these one-sided local minima, are exactly the points where you'll see some z where at some point you have genuine disjointness. And this isn't actually very hard to prove once you've kind of set up everything that we've set up so far. So I can go ahead and give my proof sketch. So basically, we want to check, the question here is for what y in R is there a disjoint geodesic in W from 0 to y and from some z to y. So the reason that this is doable is because your geodesics from 0 to y actually have a very simple structure. So just like in the melon, they've always followed the top line. When you're looking at geodesics in W, they're always just going to follow the top line. So my picture, when I try and draw what W looks like, is that these geodesics follow the top line. So now you should think about what do geodesics from Z to Y look like. Now these ones are much more complicated, right? So they are somehow doing a last passage process across these lines along parabolic paths. Going back down here. And disjointness would correspond exactly to when this purple path doesn't use any patch on the top line. Okay, that's exactly what it's going to correspond to. Okay, and so you can ask, well, when would it be beneficial never to use a top patch on this top line? So that's going to be, when is it beneficial to just stay on the second line for the whole time? And you can check that I mean, then you can check that the only reason it would ever be beneficial is if you had a one-sided local minima of the gap process between the top two lines at that point. And this is, I mean, there are details, but essentially this is the proof of that theorem. Okay. Okay, I had 2 pages for the proof sketch, but I only used 1. All right, so just like you can say this about, you know, this was a statement about left-sided local minima of your gap process. You also have a similar statement about right-sided local minima of your gap process. So right-sided local minima, these are points where instead of there being, so left-sided local minima, this was the picture. This is 0, Z, and Y. Right-sided local minima, so maybe this one, this is my ML. Right-sided local minima kind of has the opposite picture, which is 0, Z, Y, like that. And now you can ask, what about the set of true local minima? What about when ML intersects MR? Okay. So this set M is exactly the set of points where there's more than one geodesic from 0, 0 to x1. So these are points that look like this. Let me again draw the picture. So I have my starting point 0, I have my point x here. These are points that look like this. Okay. And you can kind of see why this would fit into both ML and MR is because if I go far enough in this direction, I eventually split off from the right geodesic. And if I go far enough in this direction, I'm eventually going to split off from the left geodesic. So in some sense, these x's are like branch points of your geodesic tree from 0. So what this construction gives you is that you have a correspondence, you have a gap process, G, and you have a correspondence between the local minima of your gap process and the branch points of your corresponding geodesic tree in the directed landscape. So this is, you know, I think this is, you know, this is obviously somewhat reminiscent of like the Brownian continuum random tree, that you have a correspondence between branch points and local minima of a particular function. And I don't know how far this correspondence extends, if you can say something more than this. Okay. So let me say the final thing I want to talk about is, you know, what this means at the level of the RSK bijection. So basically one upshot of this extended landscape construction is that you can say that the pair of the original Brownian motions and your melon W, that this converges jointly to, in some sense, the directed landscape and parabolic Airy line ensemble script W. And actually, so basically what you have is you have this RSK correspondence between B and W in the finite case. And we can say now we have joint convergence of B to L and W to this script W. And you can actually express W in terms of L. So you can use all of this work, you can check that you can use the same construction relating B and W to relate L and to relate the landscape and the parabolic Airy line ensemble. So you can go this way at the level of my little diagram. So what this is saying is that, you know, one, the joint RSK pair is passing to the limit. 2, 1/2 of the RSK correspondence still lives in the limit. And we kind of strongly believe that the opposite is also true. So basically you have B, you have W, you have a correspondence here, B converges to L, W converges to script W. We can go from L to W. The question is, can you go back? Okay. And the belief is that you should be able to, that this parabolic Airy line ensemble is somehow giving you all of the information to almost surely, I mean, again, this is sort of, all of these properties are almost sure, to almost surely construct the entire directed landscape on a strip between 0 and 1. So what we know, what these kind of Airy sheet theorems tell you is that you can reconstruct the values when S equals 0 and T equals 1. But the belief is that you should be able to do it at all times in between, which would, you know, And maybe I'll say the real difficulty with this conjecture is that the usual way you invert RSK in the prelimit is incredibly local. And there's kind of no chance that it passes the limit. So you need sort of a new way of inverting this correspondence. Okay, I'll stop there.
Thanks a lot. Do we have questions?
Okay, in the paper, this DOV paper, reviewing Virag, you had defined, there was some limitation on the X coordinate being positive.
Yes.
So are you also able to get past that in this more recent work, or?
So maybe I'll say we have, it's not written in the more recent work, but we have a way of getting past the limitation on the X coordinate being positive, but this is sort of forthcoming work of myself and Violet. Basically, and I can kind of tell you the answer to what happens is basically if you, okay, so maybe I can draw on the thank you page. When the X coordinate is positive, you kind of look at last passage across the Airy line ensemble in parabolic paths going that way. It's sort of the direction, this should be like root k over 2x at line k. If you want to look at the case when x is less than 0, then you kind of go in the other way. So more formally, you would sort of flip your landscape around, and then you flip your parabolic Airy line ensemble around, you have the same relationship, where you're kind of following parabolic paths going to infinity rather than off to negative infinity. Yeah, we have a way of getting around it. It's hopefully that work is coming up in the next couple of months or so.
Thanks.
So you had this kind of 4.4 condition characterization of the directed landscape, and the last one was that you had like the 1-point distribution, like for the distribution function for 1 pi times. Mm-hmm. Presumably, you think that can probably be relaxed.
Yeah. So if this is, yeah, I think that your analogy should be something like a Brownian motion here. So right now you can think of the directed landscape. Basically, the relationship between the directed landscape and the Airy sheet is very similar to the relationship between Brownian motion and a normal distribution, except with Brownian motions, you get increments. You get the increment from time, say, 0 to 2 by summing the increments from time 0 to 1 and time 1 to 2. And here you, instead of applying the addition operation, you apply this metric composition operation. And yes, there should be a characterization of the Airy sheet, for example, where the Airy sheet is, so just like, the normal distribution is the unique process where when you, add two normal distribution, or it's the unique distribution where when you add two independent normals, you recover another normal. The Airy sheet should have this property as well, where if you metrically compose two Airy sheets, you get another Airy sheet. And this should only happen with Airy sheets, maybe subject to some, again, you should be subject to some continuity or some moment constraint, something like that. And yeah, this would of course relax those conditions on the directed landscape, but we're kind of very far from that. That's kind of in the realm of a universality.
Oh, yeah, it's kind of universality. Yeah.
I guess you have a heavy tail. You have a continuum. The physicists think you have a continuum of heavy tail analogs that are maybe a bit like stable laws in the comparison you just drew.
Yeah, I wouldn't be. Yeah, so I don't know. There's this issue, like, if you try and do, say, I don't know, first or last passage percolation with heavy-tailed random variables, which have, less than 5 moments, then you should get directed landscape when Airy sheet like limits, but they're not, somehow the geometry changes. You don't expect to see the Airy sheet when you have when you don't have kind of enough moments. And yeah, I think you should see sort of a stable law set up. Again, I don't know. Some of these things have been constructed for like very, very heavy tails. but there should also be sort of some that haven't been constructed. I mean, maybe what I'm saying is not making too much sense because I haven't introduced enough background. But
all right, I think there's this Hamley Martin paper, but as you say, that's very heavy tail. So you have actual geodesics that kind of go macroscopically far from the diagonal. But I think the physicists expect there'd be a continuum family indexed by numbers bigger than 5 for somehow the moment, and then there should be some interesting structure there with things like I suppose the Airy line ensemble having analogs that maybe look locally like, I don't know, fractional Brownian motion with positive Hurst parameter bigger than 1/2 perhaps, and then the constructions you're talking about should feed into nice heavy tail type objects. So those, I suppose, are satisfying they have continuity, don't they? Like when you look at the theory of regular variation and have these characterizations of things like stable laws, then I suppose your composition law, if you just impose continuity, you would admit into that in principle this putative family of one parameter objects. So maybe you would need a tiny bit more to isolate the landscape.
Yeah, I think so. I don't know exactly. Yeah, I haven't thought hard exactly about what you might need though, but some like moment type condition.
Wouldn't the scaling relationship, like I don't think that the 1, 2, 3 is going to hold for.
No, no, that's true. Sorry.
Oh,
Yes.
yeah.
Okay. Yes, that's right. They would be a different. Yeah. Okay. Sorry. Yeah.
It might be very hard to construct the analog of the directed landscape or area line ensemble because you don't have the Gibbs property in these general contexts. So,
yeah, presumably it's not clear you have any integral structure. I don't know. Yeah.
Yeah, it's not something I think it's a very interesting question, but not something I've thought about what you can do when you have heavy but not super heavy tails.
More questions? And thank Duncan again for a very nice talk.